Welcome to the presentation on our work, Learning Reduced Order Soft Robot Controller. I am Chen Liang from Zhejiang University, and my collaborators are Shifeng Gao, Kue Wu and Jerome Pan from Lightspeed and Quantum Studio, Tencent. The control of soft robots finds abundant applications in low-cost, highly flexible robotics. However, the design of controller poses a major intellectual and computational challenge due to high-dimensional configuration spaces of soft robots. Existing techniques such as direct trajectory optimization suffers from the curse of dimensionality and incurs a high computational cost, while learning-based controller optimization methods are sensitive to hyperparameter tuning. To overcome these limitations, we hypothesize that high-fidelity soft robots can be both simulated and controlled by restricting to low-dimensional spaces. Under such assumption, we propose a two-stage algorithm to identify such reduced simulation and control spaces. In the first stage, our method identifies the simulation subspace BR, to which the robot's governing equation is restricted. BR is constructed analytically using reduced order modeling to capture the salient deformations, as illustrated below each brown column. To produce accurate simulation results, BR should contain all the salient deformations and cannot be too small. In our examples, BR can be approximately 20-dimensional. Therefore, using BR as the control space is still computationally costly. To further accelerate the optimization-based control algorithm, we propose a novel Riemannian Bayesian bilevel optimization scheme to identify an even lower dimensional subspace BC from BR. BC is optimized to maximize the performance of the model predictive control algorithm given a specific task. Once BR is constructed and BC is optimized, we can efficiently compute low-dimensional control signal FC restricted to BC using model predictive control. Our control task is specified by a reward function, under which we formulate our problem as a bilevel optimization. Our low-level optimizer is the MPC, trying to maximize the reward while being restricted to BC. In concordance, our high-level optimizer is fine-tuning BC to maximize the performance of MPC. The bilevel problem is computationally challenging, because one evaluation of the reward function involves running MPC over an entire trajectory. Further, the reward is non-differentiable with respect to BC because of the non-differentiable contact mechanism of the dynamic system and the stochastic nature of some MPC algorithms. For these reasons, we propose to adopt Bayesian optimization to solve the problem. Bayesian optimization maximizes a smooth surrogate of the reward and works well on a relatively small data set in practice. Finally, as BC identifies a subspace of the simulation space, BC should be orthogonal and thus confined to a Stiefel manifold, giving rise to our Riemannian Bayesian bilevel optimization formulation. To utilize low-fidelity short trajectories, we also incorporate our RBBO algorithm into the framework of Bayesian optimization continuous approximations and set trajectory length as the continuous fidelity. Now we summarize the main results of our work, and we refer readers to the paper for more technical details. We first run MPC under increasingly larger control spaces to demonstrate the necessity to further reduce simulation space to a smaller control space. As shown in the plots, with the dimension of control space increasing, the performance of MPC is not guaranteed to improve while the computational cost scales superlinearly. We then evaluate our method on 4 soft robots with drastically different modalities and degree of freedom to show the strength of our RBBO algorithm. We control the robots to perform 2 locomotive tasks, walking and swimming. We measure the performance of MPC under certain BC by the motion distance of each soft robot along a desired direction, where we use identity BC as the baseline. A significant improvement of MPC can be achieved by optimizing BC. We finally demonstrate the robustness of our method by analyzing the sensitivity of our method to the change of tasks. We run RBBO for the soft cross to walk along 8 different directions. Our method consistently improves the controller performance as compared with the identity baseline. Further, we evaluate the optimized BC on scenes where the walking direction is slightly different from the optimization process. Our method achieves 80% performance compared with walking along the original direction when the direction perturbation is less than plus or minus 10 degrees.